up, guys? Welcome back to another video. Today, we're going to be starting off by supposing that f is a function from a to b. And since all functions are relations and f is a function, f is also a relation from a to b. Since f is a relation from a to b, it follows that f inverse is a relation from b to a. But is f inverse a function from b to a? Or at least a function from the range of f to a. In this video, we're going to be starting to see that the answer to that heavily depends on exactly two properties of functions that will be defined as follows. If we let f be a function from a to b, then we call f 1 to 1 if and only if there does not exist an a1 in a and an a2 in a, such that f of a1 is equal to f of a2 and a1 and a2 are distinct. And we say that f maps onto b, or just is onto, if b is clear from context, if and only if, for all b and b, there exists an a and a, such that b is equal to f of a. One-to-one functions are also called injections, and onto functions are also called surjections. So if there's two distinct elements of a that have the same image under f, then we cannot say that f is one-to-one by definition. So for example, this diagram over here on the left represents a function, but it is not an injection because it is the case that there are two distinct elements of a, this one and this one, whose images under f are the same in b. So since f of this one and f of this one are the same, it is not an injection. But over here, that does not happen. So we call the function that's represented by this diagram an injection. And for another example, this diagram over here represents a function that is not a surjection, because this lonely guy over here is not the image of anything in a under f. But over here on the right, this diagram represents a function that is a surjection, because any element of b here, these three elements, are all the image of at least one element of a under f. But notice that this function is a surjection but not an injection, because these two elements of a map to this one element of b, so it's not an injection. For our last example, let's consider the identity relation on a set A. And if you don't know what that is, it's just the set of all A, B, and A2, where, A is the set that it's relation on, obviously, such that, A is equal to B. So the relation would look something like this. You can see how the first and second coordinates of every ordered pair in the identity relation is the same. That's what A equals B is for. So is this relation one-to-one or onto, both, or neither? Well, first we observe that it is never the case that two elements of A have the same image under the identity relation of A. And since that is just the definition of one-to-one, we can say that IA is also one-to-one. Well, is it onto? Well, any element of A is IA related to itself because any element of A is equal to itself. So for any element of A, there's also another element of A, either equal to or not, that it is IA related to. So by definition, the identity relation is also onto. So we can say that it is onto and one-to-one. And notice how in this definition, the definition of a one-to-one function is a negative statement because it starts with a negation. And actually, it is famously way easier to work with positive statements, statements that don't begin with a negation, when working with and doing proofs. So we need a way to express this statement into a positive one where it is easier to work with. And this theorem does exactly that and a bit more. First we suppose that f is a function from a to b. Then this theorem states that first, f is one-to-one if and only if for all a1 and a2 in a, if f of a1 is equal to f of a2, then a1 is equal to a2. And second, also a pretty useful result, that says f is onto if and only if the range of f is equal to b. So to prove the first statement, we first suppose that f is one-to-one. Then by definition, this is true if and only if this definition of one-to-one. Then, through a series of logical equivalences, we show that this statement is logically equivalent to, for all a1 in A and for all a2 in A, f of a1 is not f of a2, or a1 is equal to a2. Now, for any two statements P and Q, P implies Q is logically equivalent to the statement not P or Q. So using this in this statement, we let P be the statement f of A1 is equal to f of A2, and let Q be the statement A1 is equal to A2. So by this equivalence, this statement is equal to this statement, where f of A1 being equal to f of a2 implies a1 being equal to a2. Therefore, since this was all just a chain of logical equivalences, we can say that f is one-to-one if and only if this. I'm not trying to say that. And so for the second proof, the first step is, you guessed it, supposing that f is onto. Since f is a function from a to b, it is also a relation from a to b. And by definition of the range of any relation, the range of f is a subset of b. Then if we let b be an arbitrary element of b, then since f is onto, there exists an a and a that is f related to b. And by definition of range, this is true if and only if b is in the range of f. Since b is arbitrary, b is a subset of the range of f. And since both of them are subsets of each other, they're also equal to each other. Now we move on to the second implication of the if and only if, in which we start by supposing that the range of f is equal to b. If we let b be an arbitrary element of b, then since the range of f is b, I'm using a lot of b's and b's. Maybe I should change up the variables. So now let r be in b. Then since the range of f and b are equal to each other, that means r is in the range of f too. Then by definition of range of f, there must exist an a and a that is f related to r. Or in other words, there's an a and a such that f of a is equal to r. Then, since r is arbitrary, this works for any element of b, and which is true if and only if f is onto. Therefore, we can say that f is onto if and only if the range of f is equal to b. And actually, we can use this if and only if statement as a new definition for the term onto. But we're not going to do that because that's gay. If you let a be r not the set of -1, or just the set of real numbers without the element -1, and define a function f from a to the real numbers as f of x is equal to 2x on x plus 1. Well, is this function one-to-one or onto or both or neither? Well, if you let x1 and x2 be arbitrary elements of a, then let f of x1 be equal to x2, then this equivalence is true if and only if 2x1 on x1 plus 1 is equal to 2x2 on x2 plus 1. Then if we do cross multiplication with the denominators, we get this equation in which we can divide both sides by 2 to get this equation, where we can finally subtract x1, x2 from both sides to get x1 is equal to x2. What we've done here is that the statement f of x1 being equal to f of x2 being true implies that x1 is equal to x2. And since x1 and x2 were arbitrary elements of A, this works for any any two elements of A. And this is important because this is the definition of f being one-to-one. So now we've shown that f is one-to-one, but is it onto? Suppose that r is a real number and r is equal to 2. If we assume that r is equal to f of a for whatever a is in this set a, then by definition of f, r is equal to 2a on a plus 1. Multiplying both sides by a plus 1 gets us ra plus r is equal to 2a. And then what we've done here is subtract 2a on both sides and subtract r from both sides to get this. And then we factor out an a on the left side, and dividing both sides by r minus 2 leaves us with a is equal to minus r on r minus 2. But since r was equal to 2, we get that a is equal to minus 2 on 0. There does not exist an a in this set A that satisfies this equation. In other words, there exists an r in the real numbers, r equals 2, that is not the image of some element of A under f. So this means that f is not onto. So to answer the question from earlier, f is 1 to 1, but it is not onto. Notice how in this example, instead of proving the negative definition for 1 to 1, we proved the positive definition for 1 to 1. This is also just another example of how it is easier to work with positive statements. Way easier to do that than negative statements when working with proofs. That fact is really useful when trying to prove theorems like this, which says that if we let f be a function from a to b and g be a function from b to c, then it follows that g after f is a function from a to c. I mean, we proved that in the other video, so we don't have to prove that here. But it says that if this is true, then if f and g are both 1 to 1, then so is g after f. And if f and g are both onto, then so is also g after f. So to prove this first statement, we start by supposing that a1 is an a and a2 is an a. And I think you can see where I'm going with this, where I suppose that a1 and a2 are arbitrary elements of a. Then I prove the positive statement of 1 to 1. Anyway, since g after f is a function from a to c, then g after f of a1 and g after f of a2 must exist in C. That's all this is saying. Then we let g after f of a1 be equal to g after f of a2. In general, for any f that's a function from a to b and g that's a function from b to c, g after f of a is equal to g of f of a. So in this specific case, this means that since this is true, g of f of a1 is equal to g of f of a2. Since g is 1 to 1, by the positive definition of 1 to 1, f of a1 is equal to f of a2 from this. And since f is 1 to 1, by the positive definition of 1 to 1 again, we get that a1 is equal to a2. And since a1 and a2 are arbitrary elements of a, this works for all pairs of elements in A, which means that g after f is 1 to 1. Now to prove the second statement, we first assume obviously that f and g are both onto. We then suppose that c is an arbitrary element of c. Then since g, which is a function from b to c, is onto, this means that there must exist a b and b such that g of b is equal to c. Using existential instantiation, we let b be an element of b such that g of b is equal to c. Then it follows that b is in b, and because b is in b and f being a function from a to b is onto, that means, by definition of onto, there must exist an a and a such that f of a is equal to b. So this means that assuming c is an element of the set C, this means that there must exist a b and b and an a such that a is f related to b and b is f related to c. And by definition of composition of relations, this is true if and only if there exists an a and a such that a is g after f related to c. And since c is arbitrary, this works for any element of the set C. And by definition of onto, this is true if and only if g after f is onto 2. Onto. And thus we have proven this theorem. And of course, you must add the square. Functions that are both 1 to 1 and onto are really important in mathematics. So much so that we had to give functions that are both a name, which are 1 to 1 correspondences or bijections. So if a function is an injection and a surjection, it's a bijection. So this function represented by this diagram is a bijection. It is an injection because no two elements of A have the same image under F, and it is onto because every element of B is the image of at least one element of A under F. And in fact, you should be able to convince yourself that if there exists a one-to-one correspondence or a bijection between two sets, two finite sets, that they have the same amount of elements. So for example, these two sets are finite, and they both have 3 elements, and they also have a bijection between them. This is actually one of the reasons why bijections are so important in mathematics. I could go over the applications of them, but that's beyond the scope of this video, which is a video that is ending in 3, 2,